All right, and welcome to chapter 10. Now, in this chapter, we are going to shift gears a little bit and talk about homolytic bond cleavage with radical reactions. In chapter 10, we want to just do a couple of things in this chapter. We'll still see some omits, but let's start with section 1 here and just talk about what a radical actually is. You've probably heard the term free radicals before in terms of looking at biological systems. Radical reactions can occur. We'll talk about that in class. In this video, we're just going to be able to talk about what the functional group or the intermediate of the radical looks like, what's the three-dimensional shape, and be able to talk about some of its reactivity in basic synthetic organic chemistry. We'll get into the real-life applications like polymerization and free radical oxidations, antioxidants, things like that in the classroom. Free radicals form when bonds break homolytically. And if we remember what that meant was that there was a, single barbed or a fish hook arrow, and that's one electron moving at a time, one electron going to each atom. And so what we got were these atoms with these dots on the side. And if we remember our Lewis dot structures, that dot represents one electron by itself, one unpaired electron. That's what a radical is. It's an element that does not have a charge, but has an actual electron by itself in an orbital. Now, a double barbed arrow shows the movement of two electrons. That's what we had done before. In this chapter, we are going to be moving one electron at a time. So there's a little more arrows in our reaction mechanisms, but we have to move them one at a time because we are going to be doing homolytic bond cleavage. Now, if we remember our intermediates before, we had carbocations or carbanions. The carbocation is an sp2 hybridized carbon with an empty p orbital. That +1 charge tells us that we have an empty p orbital on that specific carbon center. A carbanion was a filled sp3 hybridized orbital. And so that carbanion is usually reactive, such as a base, such as the acetylide ion. We have an sp3 here just to show you the typical carbanion. A radical is somewhere in between. We are going to call it sp2 hybridized for this class. We are going to see it's more like a trigonal planar intermediate than a shallow tetrahedral or trigonal pyramidal. But it is more planar in nature. What that means for us is when this reacts, again, this can react from a top side to single barbed wire or from the bottom side when it's going to attack something. So racemic mixtures will form when we make chiral centers here. So just be aware of that. Anytime that we see a racemic mixture form in a product, if the radical was an intermediate, handle it exactly the same as you would a carbocation. Racemic mixtures will always form with our radical intermediates. Now, radicals are a little bit different than carbocations for sure. They are neutral charged, meaning they do not have a formal charge, but they do have an incomplete octet, and that is what makes them reactive. So just like the carbocation was a carbon with a +1 charge and was reactive because it had that +1 charge, a radical is still reactive even though it does not have a formal charge. The reason why it is reactive is because there's a carbon with an incomplete octet. We see that radicals follow the same trend as our carbocation stability. Methyl radicals and primary radicals are very unlikely to form. A secondary is better than a primary. A tertiary is more stable than a secondary. Tertiary being the most stable out of this group until we get to, you guessed it, resonance. The allylic or the benzylic position of a radical, just like the carbocation, is resonance stabilized. And so when we see that resonance, we have to be able to talk about the delocalization of that single electron, that lack of an octet. Even though we are not delocalizing a formal charge, we are able to delocalize the actual lack of an octet here across that radical molecule. Notice here the single barbed arrows. One electron from the radical is going to be shared with one electron from the pi bond. The other electron from the pi bond is going to become a new radical on the other terminal end. I'll call that carbon 3. So it is very important to be able to draw these resonance structures, as we see that resonance is the absolute best stability for a radical. We're looking at bond dissociation energies here. Now, what does decreasing bond dissociation energy mean? The lower the bond dissociation energy, the easier the bond is to break. And so what we have to be able to think about is all of these carbon to hydrogens are being imagined to break homolytically, right? Just imagine that is what the bond dissociation energy means. We took this bond and we broke it homolytically. The lower the bond dissociation energy, the easier that is to break, which means that this resulting radical is stable. So the radical is stable if the bond dissociation energy is small. It means it doesn't cost much to break it. So we do see the resonance radicals are the easiest to form. And then our tertiary radical, our secondary radical, primary radical, and our methyl radical. That's the same stability we saw before. We're going to add in this vinylic radical, right? When we think about that carbon that is already sp2 hybridized, pulling off that hydrogen in a homolytic reaction would result in a radical on an sp2 already hybridized center. So then you're thinking it's sp hybridized because it has two p orbitals, one for the radical, one for the pi bond. This is very unstable. Just like we saw in the alkyne chapter, the triple bond chapter, vinylic carbocations were extremely unstable, and we do not even think that they form. So looking at these values, we can start to realize that the easier something is to break off homolytically, that results in a more stable radical product after that reaction. Couple of different patterns, just like we've seen patterns before in heterolytic reactions. We're going to talk about these homolytic patterns as well. Klein has a very nice chart in the textbook, which we'll be filling in right here with the mechanisms. So let's follow along. Homolytic cleavage, usually initiated by heat or light. You can initiate them with a peroxide as well. We'll talk about peroxide initiators a little bit later on. What heat, light, or peroxides do is it will start by homolytically cleaving the bond. Right? One arrow for each electron, one electron for each X element there. Addition to a pi bond is another radical mechanism pattern. Notice here the addition of the pi bond is going to be creating a new sigma bond between carbon 1 and creating a radical on carbon 2. A couple of things just to note, these two arrows, I'll highlight them in green, are making the new sigma bond from the pi bond, and carbon number 2 gets the leftover electron as a radical. That radical right there. Hydrogen abstraction, it's not the same as a proton transfer because here we are not doing heterolytic cleavage. We're not actually transferring a proton, an H+1 cation. We're actually transferring a hydrogen, right? So a radical can come in and swap partners with that hydrogen. Notice one electron is going to carry from the HR bond to the X radical. That makes that new bond, and I'll try to color code here. The leftover creates the radical on R. Halogen abstraction is very, very similar. A radical can come in and make a new sigma bond with X, which would be in this case a halogen, and a new halogen radical is formed. These patterns are very tricky. We're going to practice them in class simply because our hands are used to heterolytic cleavage, and now we're trying to push one electron at a time with homolytic cleavage. Just a few more. Elimination, which is the reverse of addition, which was our second pattern in the previous slide. Elimination is still creating a pi bond. Just like in addition, we react a pi bond, elimination is still making a pi bond. However, we're doing it homolytically now. So when we look at this elimination, what's really important to note, again, I like to count my carbons. We are going to make a pi bond by sharing a radical from carbon 2 and one electron from the sigma bond on carbon 1. The rest of the sigma bond is going to make that radical on X appear. So we can make new pi bonds via radical elimination. Coupling is the reverse of pattern number 1, homolytic cleavage. Coupling is bringing two radicals together to make a new sigma bond. Now with these patterns, they're going to be put into one of three categories. And these categories are what we are going to see as our radical mechanisms in this chapter. So not only do we have patterns, but we do have categories in our mechanisms now. The three steps or the three classifications are initiation, termination, and propagation. We usually start with an initiation, then followed by a propagation. We want to make our actual reaction, make the organic product. That happens in the propagation. And then there's also a termination step. These two involve making radicals, or what we'll call quenching radicals, using them up, right? Initiation will make them, termination will finish them. Propagation is where we actually do the organic reaction that we want to. So to start us off, an initiation step is when where radical species are formed by non-radical species. So see here how we have one molecule and we are making two radicals from that one molecule. An initiation step will always involve the pattern homolytic cleavage, pattern number 1. Now, when we're looking at propagation, this was all that middle section that we just did in the patterns. Addition and elimination, hydrogen abstraction, and halogen abstraction. It occurs when we have one radical plus one molecule in the reactants, and then we make one molecule and a new radical in the products. All of these involve that. There's a radical in the reactant, there's a radical in the product. So it's a propagation. Keep the reaction going, right? Finally, our termination is going to involve a coupling reaction. It actually is where we have two radicals coming together to make one molecule. Notice how there are no radicals in this final product. It's the ending or the termination of the actual radical reaction.